Last time we talked about parent functions and graphs of parent functions, and today we are going to be talking about how we can do transformations on those graphs. So we're going to go through a number of different types of transformations and what they look like, and how you can identify them within an equation. We're going to start with vertical shifts. So a shift upward would be identified within an equation by a number, c, that's added after the parent function. Similarly, a shift downward would be identified by a number that's subtracted from the parent function. So for example, let's say you had y equals x squared. Now, if we were to transform this by shifting it up or down, let's say, for example, we had x squared plus 3. Notice that the plus 3 is outside and after the parent function x squared. So that indicates this is going to be the function x squared shifted up by 3. So we've graphed y equals x squared, and now we just take that and we shift this entire function up by 3, and there's g of x. Let's do the same for this next one, x squared minus 6. Again, the minus 6 is outside and after the parent function, so this means that this is going to be a vertical shift down by 6 units. So again, start with y equals x squared, and we're going to shift it down by 6 units. Great, so that's vertical shifts. Now horizontal shifts, this is shifting to the right or to the left. This is going to be indicated by a number that's subtracted or added inside of the function. Now, if it's a number that is subtracted on the inside, that's going to be a shift to the right. If it's a number that's added on the inside, then this is going to be a shift to the left. So let's take our cubic function, for example, y equals x cubed. Here's our parent function. And let's say you had x minus 3 cubed. So notice how here the minus 3 is inside of the function. It's also being cubed. So in this case, we would take our parent function x cubed, and we are going to move it to the right by 3. All right, and then for x plus 5 to the third, again, the plus 5 is inside of the parent function. It's also being cubed, and since it's plus 5, this is going to shift to the left by 5. So we take our parent function x cubed, and we shift it over to the left by 5. Next we have reflections. So reflections can be either in the x-axis or the y-axis, and it's going to depend on where the negative sign is. So if you have a negative outside of the function, then this is going to be a reflection over the x-axis. And if you have a negative inside of the function on the x, then this is going to be a reflection over the y-axis. All right, so we have y equals x squared. And let's say you have the negative on the outside of the function. So normally when we write it this way, negative x squared, it means that you square the x first and then you tack on the negative. So the negative is not being squared. All right, so this means that there is a reflection over the x-axis. So I'm going to take that parabola that we've just drawn and simply reflect it over the x-axis. All right, now what if the negative is on the inside? So notice how here I've put negative x in parentheses before squaring it, so the negative also gets squared. It's inside of the function. All right, so this is a reflection over the y-axis. Now in this case, because we're working with a parabola, and because it has symmetry with respect to the y-axis, when we reflect it over the y-axis, it's actually going to be exactly the same. And the last type of transformation we're going to go over are stretches and compressions. So there are both vertical and horizontal stretches and compressions. So there are going to be 4 types of transformations here. So if you have a vertical stretch, notice how you are multiplying the function on the outside by a number c when c is greater than 1. Okay, and then you have a vertical compression if you have c times f of x, but c is less than 1. Now, I'm not going to worry about any negatives because we know negatives refer to reflections. So here we're really talking about when c is between 0 and 1. And then we have horizontal stretches if you have a number c multiplied by x on the inside of the function, and c is less than 1, and a horizontal compression when you're multiplying by c inside the function, but c is greater than 1. Let's take a look at an example. So we have y equals x squared, and we know what the parent function there looks like. Let's start off with y equals 2x squared. So this is 2 times x squared, so it's 2 times the parent function. So we know that 2 is outside of the function, so we know it's either a vertical stretch or compression. And because 2 is greater than 1, we know this is a vertical stretch. So what's happening is we are taking this parabola and we are stretching it vertically. You can imagine kind of pulling it along the vertical axis and pulling it by a factor of 2. Now what does that mean? Well, I like to pick a point that's on the parent function and simply multiply the y value by 2. So for example, for our parent function y equals x squared, we know that 2, 4 is a point on that graph. So y equals 2x squared, well, we have instead of 2, 4, 2, 8 would be a point on that graph. So we want to stretch it enough so that it goes through 2, 8. And so really that's all you're doing is you're taking each point from the original parent function and you're multiplying the y value, the y coordinate of each point on that, by 2. So it ends up stretching by a factor of 2. Y equals 1/2 x squared. We have a 1/2 out in front of the parent function x squared, and because 1/2 is less than 1, this is a vertical compression. So imagine taking that parent function and pushing it down, so compressing it. Again, another way is to think of that point 2, 4 on the original parent function and thinking, where does that point end up if I compress it by 1/2? Well, instead of being at 2, 4, it's going to be at 2, 2. So you're multiplying that y value by 1/2. And so this is what our graph looks like. Okay, we'll do examples of horizontal stretches and compressions, but I'm going to clear off our graph here so that there's less going on. All right, so y equals 1/2 x in parentheses squared. So notice how the 1/2 multiplies the x and it's being squared, so it's inside of the parent function. All right, so that means that we have some sort of horizontal stretch or compression, and since 1/2 is less than 1, this is a horizontal stretch. Again, you can use a specific point from the original parent function. So again, I'll use 2, 4. And instead of being at 2, 4, now our point is going to be at 2, 1. So it's stretched horizontally. And then the last one we have here, y equals 2x in parentheses squared. 2, which is greater than 1, is inside of the parent function. So this is a horizontal compression by a factor of 2. So again, plug in a point when x equals 2, y is equal to 16. So this is going to be very, very much compressed horizontally until it's very, very skinny. So 2, 16 we know is not even on this graph here. So this is going to be something like this. Okay, let's see if we can look at some examples where we are going to combine transformations. So f of x equals negative x plus 2 raised to the third power. So there are two transformations here. We have a horizontal shift to the left 2, and we have a reflection in the x-axis. All right, so the original parent function is x cubed. So I'm going to draw that. And now I'm going to draw the transformation step by step. So you'll see a number of different things, and then I'll put the final transformation at the end. So a horizontal shift to the left 2 means I take this function, and let's say we use that 0.00 there to help us with the transformation. I'm going to shift it to the left 2, so now I'm here. And now I'm going to reflect this in the x-axis. So the part that's below the x-axis will now be above, and the part that's above will now be below. So reflecting in the x-axis, that's what the function looks like. And now there's a lot going on here because I've graphed each step. So just to make it clearer, this is my transformed function. All right, let's do another one. 2 over x minus 1 plus 4. So in this example, we see that we have transformations on the reciprocal function. So let's start by drawing the reciprocal function. All right, so we can see that minus 1, that is under the denominator alongside the x, that minus 1 we would say is inside of the function. So this is a horizontal shift to the right by 1. So let's go ahead and take our graph here, our parent function here, and we're going to shift the whole thing to the right by 1. All right, next we have the plus 4 afterwards. It's definitely outside of the function, so this indicates a vertical shift up by 4. So let's take our graph that's now green, that's the one after shifting it horizontally, and we're going to shift it up by 4. All right, the last transformation is there's a 2 there. You can think of this as 2 times the parent function. If it were inside of the function, it would be right next to the x. But it's in the numerator, so we can identify this as a vertical stretch by a factor of 2. And so now this is a little bit harder to indicate with when we're talking about a reciprocal function, but we'll do our best and we will try to stretch this by a factor of 2. All right, our last example, we have f of x equals 2 times the cube root of x plus 5. So in this we have, here's our graph of the parent function. And first we have the 2 multiplying the cube root function. So that 2 is on the outside of the function. So this is a vertical stretch by 2. Now we can go ahead and graph that, and you can think of it as in the original cube root function, we had a point at 1, 1, and with a vertical stretch of 2, we now have a point at 1, 2. All right, and then we have that plus 5 at the end. It's outside of the function, so this is a vertical shift up by 5. So now we take that green function there, and we can shift it up by 5, and that's going to be our final answer. So for these transformations, you want to list out what the transformations are in words, as that will help you when you go to transform the function. If it helps, you can feel free to do what we did here, where we took it one step at a time and graphed each transformation. And then when we finally finished all the transformations, we identified which one was the final one and made it very clear. You can erase, or you can just maybe draw it in a different color to make it clear which one is the final transformed function.